In this example problem, we're going to be doing a hypothesis test for an applicable business situation. And in every hypothesis test, you're always going to have two things. The first is the status quo. What is commonly accepted to believe the truth, some kind of point that you're looking for that you believe is the true average time of something that you do. And you're also going to have some kind of way that you're challenging the status quo, that you're saying that you believe that the true population mean of the point that you're looking for differs from that status quo in some way. And in hypothesis testing, they call this the null hypothesis, the going belief, the status quo. And the alternate hypothesis, the way that you're challenging it, the way that you're saying that that true mean average might be different. So for us over here in this example, we have a data file that shows the average wait time for the last 28 customers at a local convenience store. The manager of the store is concerned that the wait time of the store's customers is becoming too long, and she's considering hiring additional employees to have multiple registers open at all times. The manager has decided that she will only hire additional employees if the average wait time for a customer exceeds 5 minutes. And from that, we have the point that we're testing for. Right now, as it exists, they don't have those additional employees in the place. So they're believing at the store that the average wait time of a customer, our mu, for the entirety of customers, the entire population of customers comes in the store, is less than or equal to 5 minutes. And she is going to make a challenge to this status quo, to the accepted average of the store in some way. And her way is this: is it really true that right now, even though we believe this, that the average wait time of customers has begun to exceed or be greater than 5 minutes? Well, to do this test, we're going to perform it at a 10% significance level. What does that mean? You never have enough information to work with to make an absolute, unflappable determination about the information. To figure out what the average time is for all of the customers that come in the store, we need data from every single customer that walks over in the store for an obscenely long period of time. And we're not going to have that. We're only going to base it upon a sample. 10% significance level is the chance that we say that HO, our null hypothesis, isn't true, that we reject it. In this case, that we say, yes, the average wait time has become greater than 5 minutes. Based upon only the size of the sample that we have, we'll make that assumption. And then, after we get information about more customers, way more than 28 into the thousands, we find out later that we were wrong. And they call that a type 1 error. That is when you reject a null hypothesis in favor of an alternate hypothesis, only to find out later, once you have a larger bit of information to work with, that you've made an error. So our 10% significance level means we are allowing ourselves a 10% chance that we are going to make that type 1 error. So now we got this scenario set up. We are going to use the sample of 28 people to figure out if we truly believe that the true population average of every customer that comes into the store has begun to exceed 5 minutes. To do that, I'm going to need a t-statistic. T-statistic is going to help me find the probability of this situation occurring. And the formula for it is right here: x bar minus mu divided by standard deviation divided by the square root of our sample size. Well, let's get those numbers first so I can set up a nice little formula in Excel. What is the population's average weight? That's going to be, in a hypothesis test, the number that you are testing for. In this case, the point of time, the amount of time I should say, that we are testing against is 5 minutes. So let's let mu be 5. Your sample size is the size of the sample. We know it's 28 customers. If I wanted to be fancy, I could also use the count A function to make sure that I indeed do have 28 customers. So I'm just going to go and highlight all those customer numbers. I know it's going to be 28, but when I hit enter, it's going to prove it to me. Sample size is 28. I need the mean average sample, I need any of the sample's mean average wait time for this set of 28 customers that we came in. So how do you find the mean average in Excel? You use the average function. So I'm going to use the average, and I'm going to highlight all the wait times in cells B2 to B29, and it's going to come out to be 5.529 minutes. So this particular sample set that we have right here, the average customer waited 5.5 minutes roughly. But we know that not every single one of these 28 customers had a 5.5-minute wait. That's just not the way that works. We've all been in convenience stores. We've had times where we walked right up to the register, and then you go in the same exact convenience store a week later, and there's like 30 people waiting in line, and you're stuck there for half an hour. There's a bit of variation that goes on in here. Well, this is going to be the amount of variance of spread that we have in our sample. Let's find the standard deviation of all of these returns. This is the standard deviation of a sample. I'm going to use the stdev.s function for all of the wait times that I have listed in the sample of 28 customers in cells B2 to B29. And when I hit enter, this set of data we have right here has a standard deviation of 2.174. And now I have the 4 inputs that I need to find my t statistic. So I'm just going to fill these top 4 numbers that I just determined into this formula. So let's say this is equal to, open a parenthesis, x bar minus mu. So my x bar is 5.529. My mu is 5, or I should say my sample average and my population average. I'm going to close that's parenthesis, and now I'm going to divide that by, in another set of parentheses, the standard deviation of the sample, which we just determined was 2.174, by the square root of n. And I'm going to use the square root function in Excel, which is sqrt. Open a parenthesis there, grab my n of 28, and then close both my parentheses in the second half of that formula. So all in all, it's what you should be looking like right here in the first set of parentheses, x bar minus mu, divided by, in the second set of parentheses, s divided by the square root of n. And I get a t statistic of 1.287. And while that doesn't give me a point that I can compare against right now, what it's going to allow me to do is obtain my probability. We have information based upon a sample with our standard deviation of the population unknown. We only know it for the sample. So it's a t-test. And to figure out what my one-tailed probability is, well, my probability is in general, I'm going to use a t.dist function. So go up to insert function, type in t.dist, and hit go. And when you do so, the first 3 returns that you're going to get all start with t.dist. You have just regular t.dist, you have t.dist.2t, and t.dist.rt. Well, which one of these do you use? Let me close this out for 1 second. It all depends on what you're testing for. So I have this little chart on the side over here. You can have different ways that you're expecting the actual average of your population to compare to the going accepted status quo. You can have different ways that can happen. You can be testing that something is less than, that something is greater than, or something is different from. And that determines what kind of t.dist function you're going to use. In a left-tailed test, you would get the return that you wanted for the probability that your actual average is somewhere below the status quo, which is going to be this TDF green line right here. You could have a test where you are trying to find the probability that something is above the status quo, your accepted population average. Or you can have a test where you're going to have the probability that something is lower than the status quo or above the status quo. And how you determine which one you use is all about the symbol and the alternate hypothesis. In our case, we have mu is greater than 5. We want to test if something, for the probability that the actual population average is greater than the status quo. So if you have a greater sign in your alternate hypothesis, you would use a right-tailed test. If it was less than, you would want to find the probability that something is below the status quo. So you would use a left-tailed test. And if it was not equal to or different from, well, you'd want to use a two-tailed test and count for the probability of missing on both sides of your accepted status quo, high or low. But for us, our alternate hypothesis is that the average wait time of all customers that come in the store is now exceeding 5 minutes. We want to test for the probability above. We want a right-tailed test. So let me shrink that back down. I'm going to go back into my cell over here, back in the insert function, type in t.dist one more time, hit go, and I know now, since my alternate hypothesis is a greater than, I want to use the right-tailed test. I'm going to hit OK. And it's going to ask me to import put two things. The first is X. Well, X is just simply your T statistic. So we calculated that just to be able to determine what our probability is. We have our T statistic of 1.287. The other thing that I need is my degrees of freedom. And the formula for degrees of freedom is always the same. It is always n, in our case 28 in cell E3, minus 1. It's always n minus 1. So with all of that put in, I'm going to hit OK, and I'm going to come up with 0.0146, which means we think there is a 10.46% chance in this case that we are going to say that we are going to reject this HO in favor of high, reject the null hypothesis in favor of the alternate hypothesis, and end up being wrong in the long run. So your probability right there is the probability that you're going to make that type 1 error if you reject the null hypothesis for the alternate hypothesis. Well, what was our acceptable level? Our acceptable level right here is we said we were going to allow ourselves a 10% chance of making a type 1 error if we made that claim. Do we then reject the null hypothesis? Well, all depends. How does your P relate to your significance level, which is alpha in this case? And if your P is less than alpha, you reject the status quo, the null hypothesis, in favor of the alternate hypothesis. But if your P is not less than alpha, if your P is greater than alpha in this case, you fail to reject the null hypothesis. And don't overthink it. We're saying right now that we're going to allow ourselves a 10% chance of making a type 1 error. Our test statistic, going through and running these numbers, says that we have a 10.4% chance of making a type 1 error. And that chance that we are going to declare that the alternate hypothesis is true, that people are actually waiting longer than 5 minutes, only to find out later down the road when we have more information that wasn't actually the case, is higher than the allowable amount that we have. So do we reject the null hypothesis? And the answer to that is simply no, we do not. And why do we not? Because P is not less than alpha. And now that we ran a hypothesis test for this manager at this convenience store, we've determined that we do not have statistical evidence that she should hire that additional employee because everybody's waiting longer than 5 minutes on average. Now, we're not saying that's not the case. Maybe when we get, 280 customers or 2,800 customers worth of information, maybe we can run back the numbers that we have once our sample gets a little bit bigger and find out that is actually true. But given the information that we have, we do not have enough statistical evidence to support the fact that overall, not just for these 28 customers, but for every customer that comes in the store, that people are waiting longer than 5 minutes.